cost-effective solutions for the heat rejection in data centers. I would like to give you some general information before we are starting the webinar. As you can see, we have, I would advise to use Google Chrome as internet browser. Maybe if you use like a different browser at the moment, please switch over to Google Chrome. I would also recommend, if you're using a VPN tunnel from the company, to switch it off to have a more stable connection. All the microphones should be muted from the system automatically, but if you have any questions, please use the chat box on the right-hand bottom part. There's one time a public chat mode and also like a Q&A mode where you can raise questions. We will collect all these questions, and after the presentation, will be the presentation around 30 to 35 minutes, we will be answering the questions. And the presentation we will send out to all the participants after the webinar per email. With the today, we have two people in the call. It's one time Alex Smith, who will hold the main part of the presentation, and he is working in our R&D facility in Fareham in the United Kingdom, and taking care of our development for the PET system, for the adiabatics, for the dry air cooler, and he will guide you to the presentation today. Myself, my name is Kai Wirwig. I'm located in Germany. I was for 10 years the sales director for Kelvin in the UK and Ireland. I moved over back to Germany to our head office and taking care of our data center customers in Europe at the moment. With a few only like 2 slides about Kelvin. I know you joined to see the webinar. I would like to give you like a really brief overview about Kelvin, what we're doing and what we're producing. We're doing around 900 to 1 billion euro turnover a year. We have 5 different business units in which we're operating. The biggest business units which we're also talking today about is like one time the refrigeration technologies. In this unit, we are producing dry air coolers, remote condensers, for example, evaporators in different locations, and also the plate heat exchanger business, where we're producing brazed, gasketed, and also fully welded plate heat exchangers. With Kelvin, our revenue is at around 900 to 1 billion. It's mainly generated in Europe, followed by North America and Asia. And here we also have, I would like to mention, we have different 3 main laboratories for testing, witness testing for our customers to do performance testing, also for our dry coolers. We have 2 locations in Germany and also 1 location in the United Kingdom, where we can also invite our customers, or really like to invite our customers, to show the production and also to do witness testing for the units. With the manufacturing sites, I would like to show you like a few points only. Because we talk mainly about dry coolers today, and we can produce a dry cooler in different locations. We have a global manufacturing network with 25 manufacturing sites around the world. But for the dry coolers, for example, we can produce them one time in Świebodzice in Poland. We can produce them in the United Kingdom in Fareham at the south coast of the United Kingdom. And also we have a manufacturing site in France, in Vangle in northern France, where we can deliver dry air coolers up to 22 fan units, like one of the largest in the industry, which we can supply from there. As the last slide, and then I will hand over to Alex. As our products, we're not producing dry coolers. As I mentioned, we're also producing gasketed plate heat exchangers or brazed plate heat exchangers for the data center industry. And we are also doing open loop cooling towers, which you will find, which we also deliver for different projects there, also to hyperscale customers, for example, for Denmark, or maybe also hopefully in the future for Finland. Our products you find in white space cooling. We're doing customized air-to-air units, which are located above the servers, for example. We're doing brazed plate heat exchangers and liquid cooling. We're working there with companies together, also with hyperscale customers. And our main part is really the heat rejection with our dry coolers, and the plate heat exchanger is a circuit breaker. It's really one of the main parts. And here I would like to hand over really to Alex now, who will guide you through the presentation. So Alex, can I give to you?
Thanks, Kai. Yeah, thank you. Thank you for the introduction. Hi, everyone. I'm Alex. I'm a research and development engineer in the UK, based in Ferrum, as Kai said. I work predominantly with data center clients ranging from the edge to hyperscale, developing new technologies and deployments and introducing those into the market. Thank you, everyone, again for coming to our talk today on water effective solutions for heat rejection in data centers. So, how do we begin to improve water effectiveness within a data center? The path to an answer begins with heat rejection. When removing waste heat from a data center, we're faced with a number of different options, from dry coolers to cooling towers, and a number of hybrid options in between, each of which has its place given the right circumstances. Today, I'm going to be discussing in some brief detail how we can make dry cooling solutions more effective and efficient with the use of water, and how this can impact PUE as well as water usage effectiveness. I would like to just note that when I'm discussing power reductions today, I'm talking about the reduction in power consumed by heat rejection equipment in particular. And this doesn't include any power savings which would be made by the inoperation of chiller packs. So, what are the benefits of using water in heat rejection? Um, there are a number of different benefits which can be achieved by using wet or semi wet cooling, such as reduce footprint and increase efficiencies. But the most critical of these, with respect to data centers, and the ones I'll be discussing today, are the ability to prolong hours of free cooling operation by increasing the number of low temperature hours per year, offsetting peak ambience by reducing the air temperature during thermal spikes in the ambient, and reducing fan power and noise by requiring less air to achieve the same capacity. So, what's free cooling? The term has been thrown around to some degree, and there are a number of interpretations which can be found. At Kelvin, we define free cooling as cooling which requires no mechanical assistance, i.e., cooling without a chiller. Free cooling potential is how we define the number of hours within a year where a system is able to free cool. Here you can see a graph where the green area here shows the number of hours where a dry cooler is able to operate without the aid of a mechanical chiller. The light blue area is the same but for an adiabatic solution, and the dark blue little sliver here is for a cooling tower, with the red area showing the number of hours for mechanical compression cooling. On the x-axis here are a number of return temperatures to show you how changing your process thermal profile can adjust the number of free cooling hours throughout the year. So much so that in Chicago here, when we have a return temperature of 32 degrees, we actually eliminate the need for mechanical cooling entirely. And at 40 degrees, we even eliminate the need for water. And this site lends itself really well to systems such as immersion cooling or liquid-based cooling inside the white space. However, air-based solutions are also able to have an improvement. So if we take, for instance, a 20-degree return temperature with just a dry cooler, we have approximately 5,000 hours per year of free cooling. If we increase our return temperature by 3 degrees and look at using a cooling tower, we can get to nearly 7,000 hours of free cooling per year, which is an increase of 40%. Here you can see the temperature distribution for Frankfurt during a quarter of 2017, which I've included to show the effects of wet bulb temperature and how we can use this to our advantage. We know that ambient temperatures are sporadic and ramp up and down with time, which can be seen here. When designing a unit for a site, peak temperatures have to be considered. If we're going to design a dry cooler for this particular application, we have to design to 34.1 degrees Celsius, which is this peak right here. However, we can see that for the vast majority of this time period, that solution is going to be over-engineered because the average temperature is much lower. And this is where wet bulb temperatures start to come into effect. So the wet bulb temperature is the lowest temperature we're able to pre-cool the air to with the use of evaporating water. Cooling towers operate at this point instead of the dry bulb because they rely solely on the evaporation of water to cool down a process. In this case, a cooling tower is designed at 25.6 degrees Celsius instead of the 34.1 degrees for the dry cooler. However, semi-wet solutions such as adiabatic coolers and augmented units are able to reduce the air temperature somewhere between the dry bulb and the wet bulb temperatures. This is known as the effective air-on temperature and is the temperature which the heat exchanger coil sees. If we were to use a semi-wet solution consistently throughout the year, we could use the least amount of air possible to meet a desired capacity, using the least amount of fan power required, thereby improving PUE substantially and reducing noise levels. If we're able to reduce the air temperature exactly to the wet bulb, our temperature distribution for the same site would look like this. Our maximum temperature is now 25.4 degrees C, which allows us to select a more efficient design of unit and also increases the number of hours where our process temperature is above the effective air on temperature, thereby increasing the hours of free cooling. So how does this help on a day-to-day basis? If we take a look at the hottest day in this period, we can see how water can help with system ramping across that time period. So here the black line shows the dry bulb temperature as it rises and falls across the day, and the blue line shows the wet bulb temperature. And as I've said, and as we can see, this dry air temperature is increasing to a peak around 2 p.m., and falls again afterwards. A cooling system will have to adjust in order to compensate, typically by raising and lowering fan speed. This peak at 2 p.m. corresponds to a peak power consumption for a dry cooling unit. Um, and as we can see here, the wet bulb temperature is far more consistent. If we take an adiabatic or augmented solution and we turn that on at 7 a.m. and turn it off at 7 p.m. over this 12-hour window, what we actually see is an effective air on temperature which is far more consistent and in keeping with the wet bulb temperature across the period of the day. This allows us to have a much more predictable and stable design, and also a design which is able to cope with a much lower peak load, so a much more efficient design overall. We can see that with this, by turning on the water at 7 and turning off again at 7 p.m., we have a maximum temperature just over 25 degrees Celsius, which means we can have a much smaller heat exchanger in comparison to one which needs to cope with nearly 35 degrees Celsius had we not done this. By doing so, fan power is conserved and noise levels can be far more consistent throughout the period of the day. However, operating wet every day can sometimes be surplus to requirements, and instead we can conserve water and apply only when necessary. Like so. In the situation depicted in this graph, water is only applied when the ambient temperature exceeds a given set point, determined by the expected extreme conditions. The resulting effective air temperatures are shown again in black. In this case, when doing so, we can limit the air temperature to around 25-26 degrees, as shown by this blue line here. This allows for more predictability in performance by providing a safety for ambient spikes and minimizing water consumption, whilst also allowing for an increase in free cooling hours, potentially even eliminating the need for mechanical cooling entirely if the thermal profile allows. Free cooling can occur with return temperatures as low as 27 degrees in this particular case, whereas previously the free cooling would only occur at a peak when it was with fluid temperatures around 37 degrees. In some cases, using water may be one of the only solutions to enable total free cooling. In most cases, it's one of the most accessible means of reducing mechanical cooling hours. The following case studies were done on a 1 megawatt load with a fluid in at 37 degrees Celsius and return at 26. Annual energy and water calculations have been done maintaining an 11K delta T across the load. So if we take a look at Trondheim first, Trondheim's climate peaks around 28-29 degrees Celsius, as you can see here on the left. Given our return temperature of 26 degrees, a dry cooler isn't going to work all year round without a little bit of assistance. However, as you can see in this temperature distribution, the number of hours that exceed our thermal profile are very, very minimal. And so justifying a compression cooling plant and the large expense of that is very difficult for so few hours of operation. In this case, we can see that the use of an adiabatic system won't directly affect power consumption significantly, only reducing by 1 megawatt from 16 megawatt hours to 15 megawatt hours. However, it does increase our free cooling potential from 99% of the year to 100%, eliminating the need for mechanical cooling for only 44 meters cubed of water. In Trondheim, however, the only benefit of cooling towers is the marginally greater than 50% reduction in direct power consumption, going from 15 megawatt hours to 7 megawatt hours across the year. However, given the fact that this requires 401 times the amount of water compared to the adiabatic cooler, it's a very difficult benefit to justify. There are no more free cooling hours to be gained, but water is maybe more accessible in Trondheim, and because of that, it's a consideration which may occur. Whereas if you had the same situation in somewhere such as Beijing, where water is more scarce, it would be a less of a straightforward conclusion to come to. In Dallas, Dallas experiences temperatures which far exceed the fluid temperatures we're talking about. Um, Dallas has a peak of around 43 degrees Celsius and a relatively humid climate. So in this particular case, compression cooling is very likely to be required. We can see that an adiabatic solution offers a 19% increase in free cooling hours, but only a 15% reduction in power. So from 101 megawatt hours to 86 megawatt hours. Here, cooling tower is able to increase free cooling hours by a further 13%, leaving only 7% for compression cooling, whilst reducing direct power consumption by a further 76.5%, to roughly a fifth of the dry cooler by itself. However, the additional 1,139 hours comes at the cost of 3 times the water consumption of the adiabatic system. And in some cases, this may not be able to justify. Dallas does have very good water sources. They have, I think, something like 30 or 40% ground source water and surface level water. So it's a consideration that may be justifiable in an area such as that. Whereas if we take somewhere like Dubai, where we have a consistently high temperature profile, water is a lot more scarce. So in such areas, mechanical cooling is almost certainly going to be required when considering typical process temperatures of data centers. Here we're able to nearly double the hours of free cooling, but only reduce direct power consumption by approximately 15.5% with an adiabatic solution, going from 161 megawatt hours to 136 megawatt hours, and increasing free cooling potential by nearly twice. To reduce power consumption further, cooling towers require 43.7% more water than the adiabatic cooler, going to nearly 20,000 meters cubed over the year. However, the additional 6 million liters of water, in addition to the adiabatic cooler, yields a total of 6,045 free cooling hours over the year, and a total direct power consumption reduction of 127 megawatt hours across the year, which is 79% in comparison to the dry cooler. In such an area as Dubai, where, like I say, where water is scarce, it's possible that neither of these options are viable, despite the fact that they have significant benefits. I'm going to pass over to Kai for this one slide, and then we'll swap back to me.
I only would like to talk about, because you have, like, especially by a cooling tower or also by a dry cooler, you have a circuit breaker. Circuit breaker is like, for example, a plate heat exchanger. And with the plate heat exchanger, I want to like to point only out the design of these circuit breakers, also quite important for the efficiency of the system. So we can do with a plate heat exchanger, you can have an approach temperature of 1 Kelvin, 0.75 Kelvin. You can achieve really inside a type of modern gasketed plate and frame heat exchangers. If you're looking like, for example, like a range, it's like here, like on the bottom part is here, like a different range of plate patterns, and that is the fin pitch or the waves over the plate. And with the new design, more and more manufacturers producing plates which have a closer pitch, a smaller pitch over the plate, to have a high efficiency plate, high NTU values are achievable, which really has an impact on the design of the dry cooler or cooling tower. If you're using a circuit breaker which is really has a really close temperature approach, you have here, like, you can realize a smaller footprint, or you can increase your free cooling hours, or you have a lower energy consumption. By a smaller footprint, I would only like to show you what is the impact of the LMTD when we had a water return temperature of 26 degrees Celsius, 18 degrees ambient temperature. If you have a really close LMTD, you need a heating surface of the dry cooler of 1,300 square meters. If you're going now away, like, to a less efficient plate heat exchanger in between the data hall and also the dry cooler, you can increase the size to 2,000 square meters. But it's only like a small LMTD change there. So therefore, it's like to have an efficient unit. It's quite important there, because this unit, a plate heat exchanger, is normally a cheaper unit as a dry cooler. So the next thing is also, as you can have a closer follow to for the water return temperature from the data hall, you can increase your free cooling hours per year as well, as you can track the temperature really close to the water return temperature of the data hall. And that also leads really into lower energy consumption, as you can have maybe, for example, less fans on the dry cooler, or like lower fan speed to reduce your OPEX costs here. I would like to hand on really back to Alex, who will guide you to the next part of the presentation.
Thanks, Guy. So, what are the technological benefits and drawbacks of existing wet solutions on the market today? Today, I've been discussing, and I will be discussing, these three predominant solutions, though others and similar do exist. As a brief overview, spray systems are typically used for low numbers of operating hours, such as in Trondheim, where we were only needing a few hours in the year to boost our free cooling potential. Pad systems, however, are designed for operating wet for very long periods of time, or for situations where wastewater needs to be captured and handled. More like in Dallas, where there is more number of high temperature hours across the year, which we are trying to bring down. And cooling towers offer the greatest performance benefits, but are highly regulated and require many safety mechanisms to be in place. So spray systems. Spray systems lend themselves really well to high peak safety. As I've just described and I described earlier, peak temperatures can be suppressed for a low number of hours per year, offering contingency and performance benefits. Nozzle developments allow for up to a 95% water effectiveness due to very small droplet sizes and a percentage of otherwise lost water being evaporated on the fin. Through improvements in control algorithms and spray system design, increasing levels of control allow for improved water usage. Up to a 35% decrease in water consumption can be observed just by changing from a one-step to two-step regulatory control system. However, hours of operation have to be limited due to the fact that coil life can be reduced as some water can carry onto the fin and enable corrosion. In fact, just briefly, I'll highlight this a little bit further later on. But so for a spray system such as this, we can have up to four control stages, where we have just plain mains pressure and operating half of the sparges. So in this picture that you see with three sparges, you'd operate sparges one and two. We can then go to a second stage of control, which offers all three sparges. The third stage is then having half the sparges again, but with a boost pressure with a pump, and then finally boost pressure and all four sparges. So, pad systems. As I mentioned previously, pad systems are primarily intended for situations where prolonged use is required. This is due to their design being more friendly towards water management and their improved impact on coil life. The greater surface area between the air and water offered by a pad system brings larger air temperature reductions, which can be achieved as more evaporation is able to occur. This comes at a cost, as pad systems are often far more expensive than spray systems. Pad systems typically require large volumes of water to be poured over them to ensure effective operation and to minimize dry patches, which can lead to significant waste if the wastewater isn't managed. So cooling towers, though they often require many times more water than adiabatic systems, cooling towers offer the best free cooling potential and power reductions. However, cooling towers require a plate heat exchanger typically, which increases the required approach, as kind of discussed briefly earlier. Sometimes this can limit operation due to the impact it has on the thermal profile of the process. Cooling towers are often subject to many health and safety regulations and can require routine inspections to ensure proper maintenance has been upheld due to potential health risks caused by retention of water. Whereas a padded system or a spray system can have self draining qualities which minimize this risk. So we've talked about what already exists today and how we can use this to our benefit, but how do we improve in the future? I see three key routes to improving water and power effectiveness. Number one is improving through new ideas. Number two is improving through intelligent design and manufacture. And the third is, comes from improvements in the accuracy of control. So if we talk about innovation first, refrigeration has hardly changed in the last 100 years, with many improvements being innovation in manufacture and design rather than in fundamental operation. One technology, however, is beginning to gain dominance in the market. which is augmented cooling, also known as hybrid cooling. This technology involves the application of water directly to the coil block to augment the thermal characteristics of the coil and the air. Water is evaporated and heated to remove energy directly from the process as a secondary thermal sink. This allows for impressive enhancements to dry capacity, pushing units to 3 to 4 times their dry capacity. This allows them to operate in extreme climates where adiabatic coolers and cooling towers are unable to function effectively, whilst also offering the same benefits as discussed earlier, such as fan power, noise suppression, and increased hours of free cooling potential. However, this does come at a cost. Applying water directly to the fin can cause premature corrosion, and so should be accompanied by preventative measures such as intelligent control and distribution systems, protective coatings, and appropriate material selection. Augmented cooling is having more of an advent in the industry, and at least I think will be one of the next big phases in heat rejection equipment, especially for data centers. I've been involved in a number of projects all the way from the edge to hyperscale where we've looked at augmentation as a solution. It's not something that currently we provide, but it is something which is which is growing in the market and gaining dominance. And the pure reason for it is the fact that you have such a large control over, such a large ability to control the thermal characteristics of the heat exchanger. So, for instance, we were looking at a data center project in India, and one of the only ways that we were able to effectively cool that process was with an augmented solution. And I think you'll probably see this branch out into other areas, especially as people look for new innovative methods of free cooling. So this leads me to design. How can we improve water efficiency and effectiveness through design and manufacture? One key avenue is through informed component selection. Here we are comparing a newer nozzle technology to that used on earlier adiabatic systems, and we can see a greater temperature reduction with less water consumed in the process. The y-axis here is representative of the air temperature reduction achieved, while the x-axis is indicative of the volume of water consumed to achieve that reduction. This increase in performance is due to innovations in the agriculture industry, where most misting nozzles come from for these applications. And this allows us to have a reduced droplet size over an increasingly reduced droplet size over years of development, giving a more consistent and smaller band droplet sizes, as well as improved spray patterns for more effective water application. The smaller the droplet size is, the greater rates of evaporation that we have because there's a greater surface area between the air and the water. So the smaller these droplets are, the greater rates of evaporation, the greater temperature reduction we have. And this all comes from better nozzle characteristics. Sometimes, however, intelligent component selection doesn't come from component innovations, but rather from component quality. On the screen here, you can see two graphs which show the performance of adiabatic pads from two different suppliers of the same thickness of pad. The solid line here shows the supplier's catalog curve, whereas the dotted line shows the test curve from our lab facilities. As you can see, the pad on the left showed no deviation, whilst the product on the right here showed a 15% increase in pressure drop and a resulting 8% decrease in air volume for this particular fan speed. By selecting the component on the left, we can provide a more accurate and consistent product, which is manufactured to much tighter tolerances, allowing for efficiencies through the reduction of over-engineering. And that's kind of the theme that you'll see through all of these aspects is improving control, efficiency, and design. We're trying to get these small efficiencies to try and get closer and closer to applying the right amount of water at the right time. We're having systems which are not over-engineered, compensating for large tolerances. Here we go. So there's a small delay for the slides loading for me. Function and water consumption. Pad thickness is a parameter of adiabatic systems, which is often seldom considered by customers. Most products on the market feature a 100 millimeter pad, though products with up to 300 millimeters and beyond are available. Oh, there we go. So hopefully when this loads, just so I can show you with my mouse, Apologies for my terrible internet connection. There we go. So these three areas show the possible air temperature reductions achieved by a 100 millimeter pad, which is shown by the purple area, a 150 millimeter pad shown by the blue area, and a 200 millimeter pad shown by the green area. For ambient temperatures between 27 degrees on the minimum of that box and 44 degrees at the top of each one, and for relative humidities between 20% and 90%. At 20% humidity, this line here, and at 27 degrees, so looking at the bottom of each of these three shapes, um, we can see how the air temperature reduction of the pad can increase. So going from 100 mil pad, this purple one, to the blue, making this jump here, we can see we go from an 8.4 degree temperature reduction to 10.4 degrees on the 150 millimeter pad, an increase of 2 degrees. Increasing from the 150 mil to the 200 mil, we go from 10.4 degrees to 12.8 degrees, another increase of 2.4 degrees, which gives us a total additional temperature reduction of 4.5 degrees from a 100 mil pad to a 200 mil pad. So this means that at 27 degrees Celsius, 20% relative humidity, we would go from 27 degrees down to 14.2 degrees effective air on. At 44 degrees Celsius and 20% humidity, the air temperature reduction in this case can be as much as 19 degrees Celsius, bringing the ambient down from 44 degrees to 25. So how does this affect power consumption? As the effective air on temperature is reduced, less air is also required to maintain a given capacity, though a thicker pad will increase the static pressure drop on the fan, reducing efficiency and increasing power consumption. Shown here are power consumption curves given required air volume for the unit in question for each pad. So these are corrected to show the right power consumption and the right air volume given the temperature reduction that I've just talked about. So as you can see here, though the thicker pad, the 200 mil pad, has had an additional resistance because it's thicker, it's far outweighed by the additional cooling effect which is observed. So those extra 4.5 degrees actually result in about a 65% reduction in power consumption at 20% humidity, and 50% going from 100 mil pad to 150 mil pad. And this benefit, as you can see, only increases. It's important to remember that it's not always the case and that varying operating conditions will impact this effect. However, how much water will these pads use? A thicker pad will inevitably use a little bit more water. So does this outweigh the power savings that we find? And in this particular instance, the answer I think is probably no. So here we see makeup water, which shows how much water is required to replenish the system, and wastewater, which shows the volume of water sent to drain. So I'll start with wastewater, and we'll discuss makeup briefly. So there's two primary types of pad systems which exist. There are recirculation types and to waste systems, which is your standard. So a recirculation system will take uh, the wastewater and pour over itself. And pad systems require much more water to flow through them than they actually require to ensure that they're operating effectively. If you don't harness that water, it's just taken to waste. And so you can see here, a standard pad system has significant waste, nearly as much as it's using to make up, whereas a recirculation system can be as little as nearly a seventh. Um, Here we can also see that the increase in thickness has had a negligible effect on the water consumption. So we have a 100 millimeter pad, 150 and 200 millimeter pad shown across the different humidity ranges. And we can see that an increase in pad thickness does give us an additional water consumption, but it's relatively negligible considering. So accuracy, how does the way in which we control these systems affect their effectiveness and efficiency? Oh, is it not changed? There we go. So here we see a one-stage control system represented by the orange line, which would follow this green line at the bottom and come up, and a two-stage control system, which is the same here shown by the green line. Both systems turn on at 20 degrees, yet the single-stage system turns on and instantly starts consuming 1,100 liters an hour, whereas the two-stage system consumes a little over 600 before then um, going up to the 1,100 in the second stage. The blue line here represents the amount of water required in order to achieve the maximum air temperature reduction. So from this simple upgrade, we can save about 35% water, which is shown here. and this only improves as we increase control stages. So previously, I mentioned that the spray system was able to turn on and off sparges and also have a boost pressure. And so we see that here. As we increase the number of control stages now from 2 to 4, we get closer and closer to this blue curve, getting as close as we can to applying the right amount of water at the right time. We will still overspray at times and underspray at others, but the more sophisticated our control algorithms become, and the more control that we can put into a product, the less waste that we will observe. And finally, some brief remarks on how we can see the industry changing and the challenges and opportunities we face as heat exchanger manufacturers. Oh, is it loading? There we go. As I'm sure most of you are aware, there is an increasing demand on the white space. We're seeing growing compute capacities within smaller footprints, exponentially increasing the thermal demand from heat rejection systems. Considering an industry which has hardly changed fundamentally for 100 years, we have to find efficiency gains through fine-tuned refinements and innovative application of design. The growing adoption of immersion and liquid-based cooling solutions in the white space are leading to changes in process fluids, such as corrosive deionized water and viscous dielectric oils, and elevated temperature profiles. This has led to the development of tube profiling and to combat viscosity and fin refinements to improve efficiency when necessary materials offer performance losses. We're seeing customers look for innovative methods of free cooling as there is increasing socio-economic pressure on data centers to reduce power and fresh water consumption. Companies are looking to the sea where temperatures can get as low as 4 degrees at the bottom of the thermocline and a steady 13 degrees Celsius 200 meters below the surface. People are also looking into the ground where the temperature is a more stable 10 to 15 degrees Celsius, looking for ground sinks, and at altitude where there is a 6-degree drop in air temperature for every kilometer above sea level. I'm sure we've all heard about data centers planned for space. With improvements in data transfer methods, the idea doesn't actually seem too far from the present and offers fantastic cooling solutions. Uh, and finally, the nature of data hall arrangements themselves may change, causing us to reimagine how we interface with heat within the data center and how we design products to fit within the white space. Thank you guys for listening. And if you would like to find out more about data center cooling, please check out our K-focus episodes where we discuss 5 key topics. And each episode has a companion paper which is available for free for download, which goes into the topic in more depth. I think now we've got a video we'd like to show you guys, which highlights some of the manufacturing capabilities, etc. Don't. There we go.
Hello, everybody. Then,
I think there's a few questions here.
yeah, I think we should start maybe from the top, maybe. with the
Yeah.
spray system and the retrofit pad system. Yes, we can supply a retrofit also for sure for our own units. The our unit is like designed as that we can enable us to provide a pad system or a spray system as retrofit. A spray system is not so difficult to retrofit. A pad system is a different thing because with a pad system we have a module which we can bolt onto the front of the unit. For sure, we need to check the fan power because we're increasing the pressure drop over the coil, and that we need to check. But we can also not do it for our own brand. We can also do it for other brands as well. Alex, do you want to add something, or is it?
No, I think you did it quite well. So yeah, like I said, the pad systems that we have retrofittable options. They yeah, I think we're dealing with a few at the minute, which are intended for
Mm,
retrofit, and they're a
yes.
good option for sure. I mean, especially with pad systems. So the pad systems often can have quite a high capex. So
Yeah.
sometimes, especially depending on when your installation is in the year, you can offset some of that cost by having a retrofit solution later on in the future.
We're looking at some customers at the moment, like for example, like I think in the Frankfurt, it's a project where we're looking into it at the moment to fit the diabetics afterwards, because also the climate also changed over the last years a little bit. The summer's a little bit hotter, and nobody expected that in the past, really. Um, then I would like to go to the next question from Tom Carter. That is right. It's correct. It's like for the plate heat exchanger with the small LMTD, you will increase the area. Here on the slide, I meant to say it is the area of the dry air cooler. So as a dry air cooler will be have a bigger gap, a bigger temperature difference between the ambient temperature. You can have a smaller dry air cooler if you have a more efficient plate heat exchanger there located. So it was actually the surface, the heating surface of the dry cooler and not of the plate heat exchanger mentioned on the slide. And but otherwise it would be correctly on the plate heat exchanger, the area is increasing with the smaller LMTD. That's
I'd like to go to this question over here, although I wanted to kind of show a slide. We're doing it. Let me. Yeah, so for any solution, do you have a recommended server error in the temperature? So if I pull up the slide I want to show, someone might have to help me out here. One second. There we go. Right. So Um, air inlet temperatures are going to be defined mostly by any of your contractual requirements or your computing equipment requirements. But obviously there is a temperature range which is acceptable. Nothing has to be exactly to a specific degree, and you'll have impacts further down the line. So I can only speak from the heat rejection side or from the heat exchanger particularly. I don't know what impact this has elsewhere in the data center, but by increase in any way that you can increase your fluid your process profile, you have more opportunity for free cooling. So if you had, for the sake of argument, 80 degrees in and 70 degrees out, you're going to free cool pretty much no matter where you are. You don't need cooling towers, you don't need water. The lower that temperature profile becomes, the more susceptible you are to needing mechanical cooling and water, because your temperature profile starts to get closer and closer to the ambient and starts to limit your LMTD, your approach, but also limits or can, if it sinks below it, then means that you have to have some form of additional cooling to condition the air or to assist in the cooling of your process. So I can't give you a specific recommendation apart from whenever you look at a system. If it, I mean, I don't design data centers. I'm not a data center architect, but um, from a heat exchanger point of view, the higher your temperature profile can be, the more efficient your heat rejection will be. I hope that answers that.
so I think that was a good answer.
What other question have we got there, Connor?
Looking
Water
with
quality.
water
Let's talk about that one.
quality. Yeah.
Is it public? It's taking this time. There we go. So yeah, there are some restrictions on water quality. We tend to recommend. I haven't got them to hand with me. I could dig them out, and if you are interested, I encourage you to contact contact either Kai or myself, and we can discuss it further. But typically speaking, we use potable water. That's sort of where we come from. We need the problem is that the water has to have a low conductivity and low scaling. Those are the two biggest things. So with the conductivity, so mineral deposits, we then end up having to dump the water when it reaches a particular limit, and the same with scaling. So with pad systems and spray systems, but they both have small orifices in their design which can be clogged. And with pads as well, the pads themselves can build up with scale because you're evaporating water from their surface. So the lower your scale content, the better, and the lower your mineral content, the better. Um, but it does vary from site to site. And with pad systems, we tend to try and encourage people to get water quality reports for where they are, because then we can tailor the pad system much better. Um, but yeah, there are people looking at using gray
Yeah.
water and wastewater, return water, rainwater. Pad systems are generally more forgiving for those kinds of things. You just have to take those things into consideration. So you may require more maintenance. There will always be a downside somewhere.
Uh,
Um, if you
So we have also
compromise on
like a
water
strainer.
quality, but at the same
Yeah,
time, the better the quality of the water.
we have also like a
Yeah,
strainer
yeah,
in
we
the
have
system as well.
the system itself will often not just yeah, not just ours as well, but other systems will. But that will only take out large part
Mm.
particulates. Um, so any debris that's in the
Yeah.
water, but the actual quality of the water itself, the scale and the mineral deposits, that has to be controlled. Yeah. What else have we got?
Mm, that-
I think that's pretty much everything. I believe the
Um,
presentation will be sent out to
yeah.
people who are interested.
Yes, we will send out the presentation. There was one thing about the overall PUE and basic components. For sure, we can give you as we can calculate plate heat exchanger, we can calculate the cooling tower, we can calculate the dry cooler. If you're interested, we can give you different designs for the different type of equipment with different restrictions. So that is able by us to do. So we can give you a design for a dry cooler. We can give you a design also for a cooling tower, so you can compare about the water consumption. You can compare about the capex cost and like the opex costs as well. So we are able to do that as we are manufacturing all this type of equipment. For us, it's possible to provide all these designs as we are manufacturing it anyway. That was like the last questions for the PUE. Otherwise, are there any more
Yeah.
questions? Or
Yeah. Whilst any
I think
last
somebody's
questions come in,
typing.
I would just say that please check out the K-focused webinars that we've or episodes that we've posted. They and please, if you have a moment, try and read the papers as well. They have some very good content developed by our team here, who
Yeah.
experts in their field, and yeah, it gives some very
Maybe we
interesting
can go back.
insights on
Maybe we
some
can.
key
Yeah.
aspects of data center.
Yeah. If we go back maybe to the slide only quite fast. So this is the one slide. We put there quite a
Yeah,
lot of work in. Our marketing department also put a lot of work in. If you want to look, you can download the papers, white papers as well. And we present the different options what are possible for the heat rejection, but also like for liquid cooling, and also what we're doing on the air-based cooling with customized units there as well. If there are not more questions, I would thank you everybody to join us in the webinar, and that you spent your time with us. I hope you enjoyed it, and I wish you then a nice day, and I wish you also a nice Christmas period now already, and hopefully we'll speak us in the new year then. Therefore, thank you very much. Therefore,
holiday.
thank you.
Thank you. Thanks everyone.
So now.